This lecture is on electron configuration. As you can see here, all elements in the periodic table have electrons that go in and march into designated orbitals. So electron configuration is just this depiction, this overlay of how the electrons are arranged in an atom. So this is something that you actually can look up in a lot of periodic tables. So really no need to memorize. However, we're going to figure out in this lecture how we come about some of these different electron configurations. The key point that you need to recognize is that electrons march in, and they march in a specific order. So for example, the electrons are going to march into the 1s orbital. Hydrogen has only one electron to worry about, so it's going to go into the 1s orbital. Helium has two electrons to worry about, and so it's going to go into the 1s orbital, spin up, spin down. So henceforth the electron configuration for helium is 1s2. One thing you'll notice here, the noble gases, they all fulfill an octet. So all of the shells are completely full. Henceforth we give them the name noble gases because the entire valence shell of these electrons are completely filled. A couple of things before we go into a little bit of the details. This shows all the this shows all the electron configurations of all the different elements. One thing I want to remind you guys is that going across is a period. So hydrogen is in period 1 alongside helium. Lithium, beryllium, boron, and carbon are in period 2. The third row are period 3 elements, and so on and so forth. Going down, we have a group. So the columns in the periodic table are called a group. So we will call this group 1 or 1A, also known as the alkaline metals. Group 2, 2A are the alkaline earth metals. And some periodic tables have this designation. As an example, some periodic tables will call group 7A group 17, but these are also known as the halogens. So going down a column in the periodic table is called a group. Going across a row is called a period. As I said before, a lot of these electron configurations you can just look up. The point here in this lecture is just to see how we're able to get some of these electron configurations, a little bit of a better understanding of how these electron configurations are actually configured. We have the S block. This is what I mean when I said the n-1d block. So we go from 4s, and then from 4s we go to 3d, and then from 3d we go to 4p. So remember again, I want to hit the key point. Electron configurations, the electrons are going to march, and they're going to march into designated, almost like soldiers, they're going to march into designated orbitals in a very specific order. So the electrons will go 1s1, 1s2, 2s1, 2s2, then they'll go to 2s2, 2p1. We fill the p orbital. Remember, the p orbital holds 6 electrons. So we go on like this, 3s2, and then we hop on to the p's, 3s2, 3p1, 3s2, 3p2, all the way till we fill the n equals 3 shell. That's the noble gas argon, the inert gas. The key point here is that after 4s2, we go to 3d, then the 3ds are your transition metals. Then we go to 4p, fill up to 4p6. Then go to 5s2. After 5s, we go to 4d. These are the transition metals. Remember, n-1. After 4d, we fill up 5p. Then we go to 6s, 6s1, 6s2. We take a little detour here. From 6s2, we fill the 4f orbital. Okay, so the f orbital holds 14 electrons. 7 slots for 14 electrons, spin up, spin down. So from 6s2, we fill in the f orbitals, the lanthanides. Then we go back to the 5d, remember n-1, 5d orbital. And then from 5d, we go back into the 6p. From 6p, we go to 7s2. 7s2, we go to 5f. So this is the n-2 f block. So 7s2, 5s14. Then the electrons are going to march to 6d. These are the transition metals of the 6d block. And then from 6d, we go to 7p. So the n-1 is the d block, not shown here, and also something I'm not going to teach you here, the F block is n minus 2. Henceforth, we go from 6s2 to 4f14. 4f orbital and fill up the 4f orbital. Then we come back to our normal 5d and then 6p. So energies, so these electrons are going to fill up, and they're going to fill up in a very specified order. Now, as you go higher and higher and higher principal quantum number, we go farther and farther away from the nucleus. We become more valence, more outer. We also become higher and higher in energy as we go far away from the nucleus. So the electrons are going to march. So we're the first electron here. Let's take an example, iron, for example, which has 26 electrons, okay, in a neutral form. Iron will have 26. So the first electron spin up, then spin down. So we got to fill up 26 of these. And then it's going to go to third electron of our 26 will go to the 2s orbital, then 2s2. Now the 2p orbital, this is called Hund's rule. In Hund's rule, they're going to go spin up, spin up, spin up. All right? And then they'll go, instead of going to the 3s orbital, they'll go spin down, spin down, spin down. 10 electrons. So now from 2p, we'll go to 3s. So here's electron 11, electron 12, and electron 13, 14, 15. Okay, now we're going to go spin down. This is called Hund's rule. 16, 17, 18, 19, 20. All right, now 21, 22, 23, 24, 25, and then 26. Notice for the p and d orbitals, they'll all go spin up and then spin down. S orbitals, very near to the nucleus, so they'll just go spin up and spin down. They're paired. So we've accounted for all 26 electrons in iron, and all we need to do now is just write it all out, which is shown here. This is the long form. One thing that you can also do is the short form. If you realize that 3s2, 3p6 is actually the electron configuration for argon. Electron configuration for argon is 3s2, 3p6. So from 1s2 all the way to 3p6 is actually argon. So the condensed electron configuration is argon 4s2, 3d6. Actually, that's a mistake here. 4s2, 3d6. So the correct electron configuration for iron is argon 4s2, 3d6. In fact, the nearest noble gas for iron is argon. So remember, iron likes to be +2 as a charge. So don't forget, +2 means it's given away 2 electrons. So when we take away 2 electrons, we're going to take it from the s orbital. That's a rule in transition metals such as iron, and those that are in the d block. When you give away the electrons, they go first away from the s orbital. So iron +2, the 2 electrons are going to come from the s orbital. Iron +3, the 2 electrons will come from the s orbital, and the third electron will come from the d orbital. So that's argon 3d5. How about calcium here? So how about calcium here? So I went ahead and filled out all the electrons. First 1s2, 2s2, 2p6, don't forget they're going to go spin up, spin up, spin up, then spin down, spin down, spin down. Then after 2p, they'll fill up 3s, spin up, spin down. 3p, we're going to follow Hund's rule, spin up, spin up, spin up, spin down, spin down, spin down. And then finally, our 19th and 20th electron go to 4s, and spin up, spin down. For the s orbitals, they're going to couple 4s, spin up and spin down. So here are our 20 electrons. So the electron configuration for calcium is just going to be argon. Remember, 1s2 to 3p6, this represents argon. And so argon 4s2. Calcium, as all elements that are alkaline earth metals, group 2, or group 2A, they like to be +2. So they're going to give away 2 electrons, and when it gives away 2 electrons, it becomes the noble gas argon. So we say the electron configuration of calcium ion +2 is isoelectric with the electron configuration of argon. Isoelectric means same electron configuration. So these two are isoelectric, same electron configuration. All right, let's talk a little bit about exceptions. So we fill the electrons in a very specific order. Chromium has 24 24 electrons. So let's go ahead and count this transition metal, the 24. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So this, normally you would imagine this to be the electron configuration as we follow it all out, recognizing that 1s2 all the way to 3p6 is argon. So argon 4s2 3d4 should be the electron configuration of chromium, but that's not exactly correct. What happens is that you get a promotion. You promote it to a completely half-filled 3d orbital. So when you get a promotion to a completely half-filled 3d orbital, this is what you're going to get. This electron in red self-promotes. It happens totally by itself. Self-promotes to make 3d half-filled. That's a little bit more stable than the prior arrangement. So chromium has 24 electrons. Its electron configuration will be argon 3d5 4s1. So you can write it in the order of the principal quantum number, or you can write it like I have written here, the way the electrons march into their designated orbitals. So that promotion of this electron that was formerly here goes to make 3d half-filled, completely half-filled. So below chromium in the periodic table, we also have molybdenum, and below molybdenum we have tungsten. So it's pretty much the same situation here. For molybdenum, you're going to do a promotion. So instead of 4s1, because molybdenum is in the molybdenum is in the 5th row, so we will have an electron from the 5s promote to completely half fill a 4d, and tungsten is in period 6, so we have a 6s electron. One of the 6s electrons promotes it to get a completely half filled 5d. So this is a promotion to a completely half-filled d orbital. It's just more stable than the prior arrangements. Another exception to this rule is copper. So chromium, we have a promotion to a half-filled 3d orbital. So copper, having 29 electrons, will undergo a same exception. And let's just account for all 29 of these electrons one by one. So 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So remember, we got to get to 29 electrons. So we're at 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. After 4s, we fill 3d. That's the order. So 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. So this is not the electron configuration of copper. What happens is we have a more stable form, and the more stable form occurs if this electron in red self-promotes to get us a completely filled 3d orbital. So now we have a completely filled 3d orbital. Just like in the similar situation of chromium, we had a half-filled 3d orbital. Here we're going to have a completely filled 3d orbital. This is entirely a self-promotion. Down here, so we have a completely filled 3d orbital. So the normal electron configuration of copper, the long form, is not what you see because of self-promotion. It's 4s1 3d10. And below copper is silver. So here we're going to promote one of the 5s electrons to make a completely filled 4d shell. And below silver is gold. We're going to completely promote, one of the electrons from the 6s orbital to have a completely filled 5d orbital. Actually, notice here gold, we also fill up some of the f orbitals as well to get to 79 electrons. So 2 exceptions. Other than that, all the electrons are going to go in a very specific orderly manner. And that orderly manner is this. So this is called the Offball Principle. First, you're going to go to 1s, 1s1, 1s2. Then you'll fill the 2 s's, then 2p, then 3s. Okay, follow the cursor here. Then 3p and 4s. Notice what happens after 4s. Okay, you're going to get to the D block. Okay, the D, n-1 D block. Then you fill up all the Ds, 10 electrons. You go to the P block. After P, you fill up the 5s1, 5s2. Then from the 5s, look what happens now. You're going to fill the D electrons, 10 of them. Okay, and then from the D, the electrons are going to march to the 5p. So these are the elements that include in the 5p shell. You're going to include your iodine and xenon here. And then after you fill the 5p, the electrons, we're going to go to 6s, cesium and barium. After 6s, we do that detour to the 4f orbital, and from 4f back to 5d. 5d, the 6p shell gets filled. Then from the 6p shell, the 7s shell gets filled. And then from the 7s, we go fill the F block. So the 4f is the lanthanides, 5f is the actinides. Not going to talk about them. We go to the 6d transition metals, and then the 7p. Okay, notice the D is n-1. Okay, n-1 block. After 4s, it's n-1, so 3d. And then the F block is n-2. So after the electrons march and fill the 6s, they're going to go n-2 to the F block. That is the lanthanides. That is below in your periodic table. That's where we have our detour. Let's do a practice problem here as we wrap up this lecture. Ground state electron configuration for phosphorus. Okay, again, no ions here. So 15 electrons in phosphorus. So spin up, spin down, 1s. And then we're going to fill up the 2s, then the 2p's. We fill up the 3s's. And then via Hund's rule, we're going to fill up 3p's. Again, spin up, spin up, spin up. That is our 15 electrons. So phosphorus has an atomic number 15. So 15 electrons along with 15 protons. Neutral phosphorus. Neutral. And yeah, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Those are our 15 electrons. And the electron configuration for phosphorus, well, 2s2, 2p6 is actually neon, all the way from 1s2 to 2p6, that's neon. So phosphorus is going to be neon 3s2, 3p3. We call that the condensed electron configuration. What about the ion? Why is phosphorus like to be -3 as an ion? If it loses these 3 electrons, it becomes its nearest noble gas, and that is neon. So P-3 and neon, we say they have the same electron configuration, isoelectric.